Very good. All right, I had a moment of panic that Scott had turned the screen off entirely. All right, for those of you who don't know me, my name is Dr. Heather Trajano, and I am an associate professor in chemical and biological engineering. And it's my pleasure to be introducing some of the fantastic researchers that we have in Theme 4, Biorefinery Systems. But what I will say about our researchers is that we have a diverse set of expertise and research interests ranging from fuels, chemicals, materials. But what draws us all together is our emphasis on the big picture implementation. So what does it take for our lab bench projects to go to full-scale implementation? And we do that through a combination of using engineering fundamentals such as transport phenomena and sophisticated modeling approaches combined with powerful quantitative visualization tools. And what we'll see in the case studies of professors from this group is how that big picture thinking comes into play, as well as how that emphasis on model and mechanism understanding is applied. And the first researcher that I would like to highlight is Dr. Tony B. from the Department of Chemical and Biological Engineering. Tony just recently received the BC Bioenergy Sector Award, in part for his work as director of the Clean Energy Research Center, which had their research day yesterday. And Tony has many research aspects that I could talk about. The one that I'll highlight here is his work to understand what does it take for BC to reach its clean energy goals, or its decarbonization, its clean BC goals by 2030. And so in this particular research highlight, they sought to understand how growing energy demand due to economic growth in BC will create challenges to meet that energy demand with supply. And really the key message here is that we will need greater green electricity production and more bioenergy production, and optimizing the application of both. Tony works in close collaboration with another number of other researchers on thermochemical conversion of biomass to biofuels in various forms. We have Dr. Nyoko Ellis, Dr. Jim Lin, Dr. Kevin Smith, and Dr. Shahab Sokin-Sanj, who all contribute to these areas in their own particular way. When we talk about thermochemical conversion, we have a range of severities. We can look at gasification, pyrolysis, or torrefaction, each of which produce a product or service which displaces a petroleum equivalent. But these technologies have advanced beyond the lab bench to pilot scale implementation here at UBC. One example of that is the gas pulsating fluidized bed microwave catalytic pyrolysis reactor, which can handle 30 kilograms per hour of biomass feed. A lot of other researchers here, we work with grams of biomass per run, and so this is a substantial step up. Another example of this sort of infrastructure is our two-stage fluidized bed that's capable of using either steam or oxygen as the oxidant for gasification. Again, large-scale feed, and using that same fluidized bed for torrefaction. All right, so now shifting slightly, we have Dr. Bhushan Gopalani, who leads the Data Analytics and Intelligent Systems Lab. Dr. Gopalani, in addition to his researcher hat, has been Associate Dean for Education and Professional Development in the Faculty of Applied Science since 2017, but was recently appointed as the UBC Vice Provost and AVP for Faculty Planning Pro Tem just earlier this year. As his lab group, or his name suggests, the Data Analytics and Intelligent Systems, large data, machine learning, process control are primary themes in the lab. The example that I've highlighted here is some recent work with Dr. Ripon, where they looked at how to visualize the formation of rings inside a rotary lime kiln. So for those who are not familiar with kraft pulping, one of the unit operations is to convert calcium carbonate back to calcium oxide, and this is key to chemical efficiency and minimizing environmental impact in the kraft pulp mill. But one of the challenges that builds up there is that we can have deposits of lime particles and mud on the wall of the kiln. This reduces process throughput and results in the need to purchase fresh lime, unplanned equipment shutdown, or equipment damage, all of which are extremely expensive incidences to cope with. Dr. Bruchon's team has used the data from infrared thermal cameras to identify ring formation early on, and also to help identify the operating conditions that minimize or limit ring formation. So we have this lovely purple and red diagram showing temperature as a function of time and position within the kiln. By using those advanced visualization strategies, they were able to successfully detect ring formation. And earlier, or just a few months ago actually, that technology was commercialized by Blue Marvel in their new Heat Seeker product, which will allow energy savings and reduce emissions. So again, that deep process understanding leads to advances. Next, we have Dr. Jack Sadler, who probably doesn't need much introduction, but we will anyways. Jack has been in the BC bioenergy sector for many, many years. He was recognized with the BC Bioenergy Sector Award last year. He's also served as the task leader for the IEA Bioenergy Task 39, decarbonization of transportation fuels, for many years. And the highlight that I'll draw your attention to here is his leadership in the BC Sustainable Marine, Aviation, Rail, and Trucking, or BC SMART Fuels Consortium. The emphasis here is to develop low-carbon fuels for these long-distance transportations by leveraging BC's advantages. So for example, our existing policy and the existing forestry supply and forestry expertise. There's two key goals here. The first is the software solutions, as they call them, so expanding and building on our existing policy strengths, and the hardware solutions that expand and leverage our existing strengths in feedstock supply, forestry expertise, and biocrudes and co-processing with the Burnaby refinery. Now I'm going to shift gears and introduce Dr. Sumi Sadiqua from UBC Okanagan. Dr. Sadiqua leads the Geomaterials Research Group. She's previously been highlighted for her work on pulp mill waste hitting the road instead of the landfill. And this specific example is the use of pulp mill fly ash as road construction. What they find is that pulp mill fly ash improves the adhesiveness of the other road materials, thus improving road performance. They also see very little to no chemical release from the pulp mill fly ash, a key safety concern. And so this is an excellent example of large-scale problem, pulp mill fly ash, with large-scale solution. The example that we'll highlight from her recent work is this paper here, an application of BIFs to hydroxyethyl terephthalate, or BHET. BHET for landfill covers. BHET is derived by depolymerizing polyethylene terephthalate, PET, one of the most common plastics in our recycle bin. And we mix that with sand and bentonite, or clay, to prepare landfill covers. Landfill covers have a number of technical challenges that have to be solved. We need to prevent water flow through the landfill cover, because then that will carry contaminants away from the landfill. But we also need a landfill cover that will retain water, because as it dries, it can shrink and crack. Cracks, of course, will allow more water to flow into the landfill. We also need to have high strength to resist the challenges of the environment. And what Dr. Sadiqua and her postdoc were able to show is that by adding this BHET, they can improve performance on all of these metrics. And not just, they tell you not just how they improve those metrics, how much, they can explain why it improves, and that will guide further development of the technology. Next, I'll introduce Dr. Tarani Solati from the Bioproducts Supply Chain Management and Optimization Group. I think a lot of us BPI researchers assume that when our lab-based technology is ready to go to the real world, that there'll be enough biomass, the right quality of biomass, at an appropriate cost. That's a pretty big assumption, Dr. Salati actually keeps us honest on whether or not that is true with parts of her research. And I'll highlight here this robust optimization of forest-based biomass supply chains for syngas production. So we can all imagine, we all understand that biomass supply chains have a lot of risk. Is there enough biomass? How much will it cost? The seasonal variation of that biomass. And very often the studies that have been published focus on those questions at a strategic level, at the big picture level. But when you move down a level to the tactical level, there are other considerations that are glossed over at the strategic level. In this particular paper, Dr. Salati took a close look at the tactical level and identified some oversights that weren't obvious at the strategic level, and as a result was able to model and develop a supply chain that would produce a reliable amount of biomass for gasification. And we have all seen what happens when supply chains get disrupted in a very personal way over the last few years. The results of this work, though, also says that the biomass is going to have to come from farther away and at a slightly higher cost than what we previously thought. This is an important piece of knowledge to have early on, rather than once you build your gasifier and now you don't have enough biomass to run your gasifier. And finally, for myself, I lead the Trajano research group. If I talk about how my big picture thinking gets implemented, that big picture thinking is implemented in the focus on hemicellulose and extractives, so aspects of biomass that aren't part of the main fiber line in existing industrial operations, but also in byproducts. So for example, the mechanical pulp fines, and my group has done quite a bit of work over the last few years with the Energy Reduction in Mechanical Pulping Consortium. We also focus a lot on models and what we can learn from that modeling. Recent publication from my group, we predicted xylose yield from the pre-hydrolysis of hardwoods using machine learning. There's very deep literature on recovering xylose from hardwoods. Specifically, we recovered 1,955 data points. Those were some very patient undergrad students. And then used that to develop kinetic models and machine learning models to predict xylose yield. We found that the artificial neural network model could predict xylose yield with an accuracy of plus or minus 6%, so on par with experimental results. It also helped us identify some key physical components, classic ones like temperature and time, but also some underdeveloped ones such as particle size. This work also highlighted to us the importance of developing hybrid models that will combine the physical insights of kinetics with the machine learning statistics abilities. All right, good. All right, so as I finish up here before I pass it over to theme 5, I've given you a very high-level snapshot of the excellent work from our researchers. I encourage you to take a closer look at work from our theme 4 researchers in the poster sessions. I've highlighted as many of them as I could find here. In particular, please take a look at D12 and D13, which come from Dr. Shahab Sokansanj's group. And with that, I will pass this over to theme 4, or theme 5.